Experiment, we're going to be measuring G, or the gravitational constant, using a simple pendulum. Okay, so here is a diagram for a simple pendulum. All right, so we take this ball of mass m, all right, and it's tied with a string of length L. Okay, and we're going to release this ball at some angle theta, some initial angle theta. Okay, and so we want to describe this motion, right before we let it go, okay, right before we let go at that initial angle, all right? The way we describe this motion is we're going to use Newton's law, all right? So we look at all the forces that are going on this pendulum, or on this ball of mass m, okay? So there's only two forces, actually. There's the force of the string, or tension, okay? It's labeled as TS in this case. I don't know what that S is, but it doesn't matter. So we have the tension of the string, and we also have the force of gravity, which always points down from the center of the ball, okay? And so the way we want to orient our coordinate plane, all right, just so we can make analyzing the motion of the pendulum easier, is we tilt it in a way to where the y coordinate points in the same direction as the tension of the string, okay? And so when we do that, we have to split up the gravitational force, okay, because we want to make sure our forces line in the direction of our coordinate plane, all right? And so the way we split up the gravitational force is we have an x component that's going to point in the direction of where this pendulum will accelerate, and we're also going to have a y component that's going to point in the very opposite direction of the force of the string, all right? And based on that angle given, the y component of gravity will be mg cosine of theta, and the x component of gravity will be mg sine of theta. Okay, so using Newton's second law, all right, we can write out the equation of forces for this pendulum. So in the x direction, we have mg sine of theta, okay, and because that's where the pendulum is accelerating, that's going to equal to ma. Whereas in the y components, we have T, which is the force of the string, tension, minus mg cosine of theta, because remember, the y component of gravity is directly opposite of tension. That's why we have T minus mg cosine of theta. And because this pendulum is not accelerating at all in the y direction, it's going to equal to 0. Okay? So this formula we're not really worried about. We're looking at the x component. Mg sine of theta is equal to ma. Okay, because that's where the motion of the pendulum will be. All right? So here's the same diagram, only in the other direction. But we have mg sine of theta is equal to ma. Okay? Now, if we release this pendulum at a small angle, okay, at a very small angle, then sine of theta can be approximately equal to the theta. Okay, so we can approximate sine of theta for small angles as approximately theta. So whatever initial angle we release this pendulum at, that is just what theta is. Okay. This involves a bit of calculus, so don't really worry too much about where it comes from, but we can rewrite that equation as ma is equal to mg theta, okay? So ma is equal to mg theta, all right? And we can use the displacement of the pendulum, the arc length, okay, is equal to L times theta, right? So we know L times theta is the arc length of the pendulum, where L is the length of the string and theta again is the initial angle, okay? So we can substitute that in and we get A is equal to G times X over L, okay? And we can get a harmonic oscillation relation for this one, all right? This involves calculus, so don't worry too much about where it comes from. But we can get the angular velocity of the pendulum. Okay, so that's what that Greek letter omega is. That looks like a W, angular velocity. Okay, or how fast this pendulum is moving. All right, that's what angular velocity is equal to the square root of g over L. Okay, so how fast the pendulum is moving, angular velocity, is equal to square root of g over L. Okay, so we can get the value of the period of this pendulum. Okay, so angular frequency is another word for angular velocity, but that's equal to 2 pi over the period, all right? And we can finally have a relationship for the period of the pendulum as equal to 2 pi times square root of L over G, okay? So the period is a unit of time, okay? It measures in units of seconds, okay? And what the period is it's the time that that it takes. So it's the time that it takes for this pendulum to go one full cycle. Okay, that's what a period means. All right. So anytime you have a period for some kind of oscillatory motion, right? Because again, the pendulum follows that oscillatory motion. It goes back and forth, right? The period just means how long it takes for it to go one full cycle. So it's going to go, if we release the pendulum, it's going to fall, it's going to go all the way back, and then it's going to go all the way back to that initial position, okay? So that's the, one full cycle. So how long that takes is one period, all right? Which is equal to 2 pi times the square root of L over G, okay? So based on the period, it seems like, from our theory, that if we vary the length of our string, okay, the longer the length of the string of our pendulum is, the longer our period will be, right? And the shorter the length of the string, the shorter the period will be, okay? And so we want to test this, right? According to our theory, this is what the period of our simple pendulum will be, okay? So we want to test this theoretically, right? That's the point of physics lab, okay? We have this theoretical equations. We got to test the experiment. Okay, so we're going to use a simple pendulum in our experiment, all right? So here we have an uncalibrated pendulum. So when we calibrate it, we want to make sure the string is, aligned at the perfect 0-degree mark when it's at rest, all right? And we want to test 3 different dependencies for our pendulum, okay, just to make sure our theory holds true. So we want to make 3 different graphs for our pendulum, okay? We're going to see if there's a mass dependence for our graph, for our pendulum, okay? Does the mass of the ball, does that going to change the period of our pendulum? Does the angle at which we release it at change the period of the pendulum? And finally, a length dependence, right? If we vary the length, is that going to change the period of our pendulum, okay? So we're going to have 3 different experiments for our 3 different graphs, okay? So the first experiment, we're going to test the mass dependence, okay? Or does mass depend on the period, all right? So if you watch the experiment video, okay, the TA used 3 different masses, all right, while keeping angle and length the same, okay? So they fixed the angle and the length of the string, right? They released the pendulum at the same angle for each of the 3 masses, okay? And so for the graph, you plot period versus mass, okay? So mass is our independent variable, and period will be our dependent variable, okay? So period will go on the y-axis, and the value of your masses will go on the x-axis, okay? And then we want to ask ourselves, based on our graph, is there a relationship for period, right? Does, mass depend on period, okay? So the TA in the experiment video, he times the period for a pendulum, right? He times how long it takes for this pendulum to go a cycle, okay? So those values are going to be used for your y-axis. And then the values of the masses will be your x-axis, your independent variable, okay? One thing I wanted to mention is in the video, they will measure the period for 5 cycles, I believe. I think it's 5 cycles, okay? And that's a normal thing we do in these experiments, right? Because it's kind of hard to get an accurate measurement for exactly one period, right? There's a whole kinds of, slew of random errors that you can get for measuring the period of the pendulum, right? Because, it goes really quick, okay? So we do 5 cycles, okay, in order to minimize that random error, all right? So the TA, I believe, he explains it, but I'll explain it here as well. So he times the pendulum for 5 cycles, okay? So that is the value for 5 periods, all right? So you want to make sure in your data sheet where it says 5T1 or 5T2, okay? Because, they do this measurement multiple times, okay? So we can get, a graph for it, as well as uncertainty. But you want to make sure, you're looking at for one period, okay? So if there is a value for 5 periods, make sure you divide it by 5 in order to get the value for a single period. That way you can plot period versus mass correctly, okay? So he explains it in the experiment video, but I thought I'd mention that here, okay? Just so you guys don't make that mistake, all right? But anyway, moving on. So that's mass dependence. There's also an angle dependence, all right? So that's the second experiment or the second graph that you'll do. But you're going to vary the release of the angle of the pendulum, okay, while fixing mass and length, all right? So you'll pick a specific mass that you want to use. You'll pick a specific length that you'll keep the pendulum at, okay? And you're going to release the pendulum at different angles to see if it affects the period, okay? And so your independent variable will be angle, and your dependent variable will be period, all right? And there should come a point where your small angle approximation breaks down, okay? So remember in the theory we approximated sine of theta as approximately theta, okay? And that's only true for small angles, right? But at some point, that's going to break down. So in your graph, you have to ask yourself, where will that break down, all right? Then the final thing that we're going to test, okay, is the length dependence. So we're going to keep mass and angle the same, but we're going to vary the length of the string, and we're going to ask ourselves, does this affect the period, okay? So yeah, the recorded periods for each of the trial, for each of those experiments are in the data folder, all right? And you're going to be calculating the average period as well as the uncertainty of period for these experiments, okay? So remember, the uncertainty for period, if you have, multiple different period values, that's just going to be the standard deviation of mean of period, okay? So 3 graphs for 3 experiments, okay? Now, for the length dependence, okay, I wanted to mention this one, okay? Because it's not linearized if you do t versus L, right? Remember in the earlier equation, we had t is equal to 2 pi times the square root of L over g, right? But we said L is our independent variable, and we can't just plot that because L is, underneath the square root, right? It's not linearized, okay? In order to linearize this equation, we have to make sure our independent variable is a first power, okay? So if it's underneath the square root, it's obviously not a first power, right? Square root is the same thing as being raised to the 1/2 power, okay? So how do we linearize it? Well, it's easy. All we got to do is square both sides of our equation, okay? So our new linearized equation is t squared is equal to 4 pi squared times L over g, okay? Where that g, okay, that's how we're going to calculate our experimental g, all right, based on this graph, okay? So you're going to plot t squared versus L, okay? So your L is your independent variable, right? And your t squared, that's going to be your dependent variable, okay? That's going to be your y-axis values, okay? So you'll have the values of your period, all right? And you just square it in order to find the t squared, okay? And the uncertainty for t squared, okay, that's a little bit different, okay, because that involves a bit of error propagation. I'll let you guys figure that one out, right? You guys should be able to figure it out because based on the last worksheet, you found the uncertainty for x squared, right? So hopefully, if you did that correctly, you should be able to find the uncertainty for t squared, okay? And then from this graph, this is the graph that you'll solve for g, okay? Because here we have, right, our slope is 4 pi squared over g, okay? If we were to plot t squared versus L, our slope is 4 pi squared over g, okay? And from your line of best fit, remember, if you use, Sci-Davis or a different program, the line of best fit from your program gives you the value of your slope, okay? As well as the uncertainty for your slope. Okay, so you can use that to solve for g, right? Because 4 pi squared over g is equal to slope, right? So g is just equal to, 4 pi squared over the slope if you solve for g, all right? And the uncertainty for g, that's going to involve a bit of error propagation, okay? So hopefully you guys kind of understood that in the last worksheet. But to solve for delta G, it's based on the value of your slope as well as the uncertainty for slope. Okay, so I'll let you guys try to figure that one out. All right, but that's it. Okay, so for this experiment, there is 3 graphs. All right, and this is the last graph that you're going to do all the analysis to. Okay, because this is the one where you can solve for G as well as the uncertainty for G. Okay, so that should be it for this lab. Hopefully that made sense, right? You're going to have 3 different graphs, okay? And I hope the worksheet is pretty self-explanatory from this video, okay? But this is the first real experiment that you guys do in this lab, okay? You guys do graphs, uncertainty, error bars, you'll do things like confidence and agreement, right? Because you're comparing your experimental G with your theoretical G of 9.8, okay? So this is the first actual lab that you guys do for Physics 1. So if you have any questions, please feel free to ask and stop in on the office hours, okay? Because it can be, it can be a little bit overwhelming if you're new to all this stuff. So we want to make sure we help you guys, okay? So good luck on the worksheets, and please ask questions if you need it, okay?